0. Welcome, my dear learners. My name is Mr. Mlamko Isaac. I'm going to be taking you through Waves O-Level, and this is Namugongo Secondary and Vocational School. I hope you learn something as we go through this session. So, we are going to start off with some of the things we want to achieve in this tutorial or this session. So, we want to look at the objectives. 1, the learner by the end of this session should be able to define and know what a wave is. Secondly, the learner should be able to know the characteristics of what a wave is. We shall also be able to classify waves and also describe the waves. Describe some of the terminologies used in waves for this session. So, what is a wave therefore? We've all been to the ocean and we've sometimes played in water. What do you observe when you throw a stone into water? You will see a pattern of water moving, following a shape. This is what we are terming as a wave. So this is the kind of wave. Sometimes we've used ropes when we are playing games as children. We rotate or we swing the ropes up and down. This pattern creates a form of a wave. And this is what we want to look at in physics. So a wave is a disturbance in a given medium which is transferred from one point to another without the actual displacement of the medium itself. So the medium particles remain at that position, but we transfer energy. Examples of waves, as I've started in the video, we can have waves formed on water. So we can call them water waves. We have waves formed on streams, or you can say rocks for that case. We can also have waves that are formed due to vibrating objects like drums. So these are the sound what? Sound waves. So we also have sound waves. So with these 3 examples, we can get an idea of what a wave is. We also move on to look at some of the characteristics of these waves we've defined or we've given down as examples. Waves, 1. If you're looking at a wave, one characteristic we can look at reflection. What is reflection? With reflection, we are meaning bouncing back of something or of our wave after hitting a given surface. As I am speaking, my voice creates sound waves which then move on to a given object, for example, a wall. It will hit the wall and bounce back. That bouncing back effect is what we are calling reflection. So this is the characteristic of waves. Secondly, we can also look at refraction. Under refraction, waves will change their speed as they are moving from one medium to another. For example, if you remember, we have objects and different instruments that can be used to measure sound speed. Now, in submarines, they use this characteristic by sending waves down. As these waves move through the deeper layers of water, they will meet different depth of water. And in so doing, they are going to be diffracted from one point to another. So this is also a characteristic we look at. Next we have another characteristic which we can call diffraction. Diffraction. Now with diffraction, say we have a wall and this wall has an opening. So this is our wall. The waves will be produced from a given source. When they are produced, they will propagate or move. When they reach the wall, which has a small hole or an opening, they are going to undergo what we call diffraction. Now, with diffraction, they will hit the boundaries of the wall and then they are going to be diffracted at different angles. So, here it will move in this regard. So we are producing a wave which is going to move in this regard. The best option where we use diffraction is when we have more than one hole. So we shall see a pattern created where we have the waves intertwining. So that is a characteristic we can also use. Lastly, but not least, under the characteristics, we have what we call interference. Interference. So when we go to discourse, when we go to theaters, we hear different sound notes. These sound notes are created because of interference. Where we hear low sound notes, meaning there is no sound and there is destructive interference. Where we hear sound notes that are high, then these are what we call constructive waves, which are caused by constructive interference. So these are our four characteristics of waves. Now, after understanding the characteristics of waves, we can move on and say, are there types of waves? If they are there, how do we then classify these waves? So we can look at what we call a classification of waves. Classification of waves. So we have classification of waves. Waves are classified in two ways. The first way we classify them with, we can say we have mechanical waves. The second way, or the second classification, is electromagnetic waves. So these are the two classifications of waves that we have. So we are going to break them down and look at one by one. Mechanical waves. What are mechanical waves? These are waves produced by vibrating bodies. They are transmitted by particles of the medium vibrating about its rest position. Take an example. When you hit a drum, or if I hit this board here, you hear a sound. This sound is created because the particles of the board are vibrating as a result of me tapping there. So this is what we are calling a mechanical wave. These waves require a medium. One, they are brought about by vibrating bodies. Two, we are also saying they require a medium of propagation. Require a medium to propagate propagate. So what do we mean here? For these waves to be transmitted from one point to another, they need a medium. These mediums could be solids, could be gases, or liquids. For example, I gave an example of a water wave. For the water wave to travel from one point to another, it needs that medium, which is water. So we are seeing the water wave moving from one point to another. So the wave will be transmitted. This is what we are meaning. If we have a rope, the rope could be tied at one point. So someone is handling the rope at this point. When they dangle the rope up and down, it creates a pattern of a wave. This rope, therefore, is a medium, and this is what we are calling a mechanical wave. We move on to the second example or classification. It is electromagnetic waves. From the word itself, you have electro and magnetic. So, for you to easily define or talk about these are waves that are created due to the vibrating component of the wave in terms of electric and magnetic form. So, this wave has both electric properties and magnetic properties. So this is what we are looking at. These waves, not like the mechanical, do not require a medium. Remember we said these require. So these ones do not require a medium for them to propagate from one point to another. In other words, they can travel through vacuum. That is how we are able to get waves or to get some rays from the sun through the vacuum of space to Earth. It is because the light waves are electromagnetic waves. Other examples apart from the light rays, we can also have ultraviolet, which falls under that. So we have X-rays. These are also electromagnetic. We have gamma rays. These are also electromagnetic waves. So after looking at the classification of waves, then we go ahead to see a graphical representation of how a wave looks like. I've already given you one sample of a wave of a string. But now we want to note some points that we are going to talk about in this graphical representation. So if I sketch my diagram, we have that. So we have displacement, we have the wavelength. So how can we measure wavelength? We can measure wavelength in two ways. Can have that. This one is in time. This is displacement. We also have the time it takes still the wave to move or to make a complete cycle. We shall denote it there. And that will give us what we want. So we have this line here, or which we are calling the time axis. This is what we are calling the rest position. Rest position. Rest position. So this is our graphical representation. Now we want to go in detail and look at how we can describe or explain these terminologies. The first one we shall look at is the amplitude. This displacement from the rest position up to the point where the wave reaches its maximum is what we are calling the amplitude. So how can you define the amplitude? You can define the amplitude as the greatest displacement of any wave particle from its equilibrium, or what we call the rest position. Equilibrium, or what we call the rest position. We then move on to look at what we call the wavelength. So that was amplitude. We are defining amplitude, and it is normally denoted as the capital A. So we have what we call the wavelength, normally denoted by that symbol we call lambda. The wavelength is the distance between two successive particles in a wave profile that are in phase. So if a wave particle started moving from here and it completed its first cycle from the rest position to a rest position, then that distance we are going to say is the wavelength. If for another case we can also define it in terms of the distance between two successive crests or troughs. So what is a crest? The maximum point of displacement, and the trough is where we form the maximum, but in the opposite direction. So if you have 2 points and this particle moved from one crest to another crest, then we are going to say that the distance between these 2 points is what we shall call lambda. So this is another crest, or 2 troughs, as we have said. So this is how we can define the wavelength. If we look at another term, we can have what we call the crest. We finished. We can have what we call the period. Period is this capital T. So look at our diagram. We are looking at the first point up to where the wave will make one cycle. So in other words, we can define the period capital T, the period capital T, as the time it takes for the wave to complete one complete oscillation. Period T is the time it takes the wave to complete one oscillation. So if this is capital T, then we shall denote it time taken to complete one oscillation. So meaning the time out of the number of oscillations, we form our period. We also go ahead from period, we have what we call the frequency. We have what we call the frequency. We denote it as small f. Frequency. Frequency, this is the complete oscillation per given second. Complete oscillation per given second. So, a frequency, if we want to write it in terms of mathematical expressions, we are going to say f is equal to the number of oscillations out of the time it takes, and we are saying an oscillation per given second. This is what we are calling frequency. So we have those. Then we look at a cycle, or what we call an oscillation. A cycle or an oscillation is when, if I denote this with A and B, for us to have a cycle or an oscillation, this is the to and fro movement of a particle from one point to another. We call it a cycle or an oscillation. In this case, we have movement from A to B. The wave will undergo half a cycle, and it will complete its cycle when it moves from A to B. This is what we are calling a cycle. Okay, so that is the graphical representation of a wave in summarized format. In summarized format. So, we want to look at relationship between F and T. But we've said our F is the frequency and our T is the period. If we combine this, what we get, how can we relate this? Because when we look at calculations in waves, we shall require some derivations from the combined expressions of period and F. So, if we go on, remember we say the period is the time it takes for a complete oscillation. Frequency is the number of oscillations per given second. So, we want to combine them. Now, allow me call this equation 1. From here, t is equal to small t out of n. And also allow me call this equation 2. So we form two equations from our expressions. Capital T is equal to small t divided by n, and F is equal to n divided by small t. Now, we want to get a relationship between F and T. We are going to multiply these two equations. Mathematically, we realize that T and F are related. How? If you look at the letters that are expressing T and F, they are the same. What do you analyze? You analyze that they are inverted. So for us to multiply these two equations, it means the expression can either increase or decrease. So we shall say equation 1 multiplied by equation 2. Equation 1 multiplied by equation 2. So we've given these equations numbers. So we go ahead to multiply. So equation 1 is capital T multiplied by small f. When you multiply this, we are first starting from the left hand side of these two. So we shall multiply 1, which is T times f. We go ahead. On the other side of the equal signs, what do we have? We have, so this will be equal to T small divided by n times small n divided by t. So this part here is for the capital T times the part for the small f, which is n divided by t. So analyze this very well, because that's what we are doing. Another person can go ahead to divide these equations. They will end up coming to where we want to go. So whether you divide or multiply the two equations, we shall reach our destination. So let us continue. When you multiply on the left, we shall get TF, and when we multiply on the right, so we know some math, when we are multiplying and we have similar characters or values, they can be divided. So we have T and T. So this T will reduce with this T to give us 1, and N will also reduce with this N to give us a 1. So what do we get? In the end, we shall get a 1. We end up with a 1. So we have that when we multiply equation 1 and equation 2, we get a 1. What does this mean? Remember, we are looking at the relationship between F and T, where our F is the frequency of the wave and T is the period of the wave. So the relationship, therefore, if we wanted to say that make T the subject, we shall divide through by F. So we shall have divided by F on both sides, 1 divided by F. This leads us to the period being equal to 1 divided by F. This is the relationship between F and T. Now when you look at this period, it is inversely proportional to the frequency. If we look at our inverse proportionality, we have that T is going to be inversely proportional to F. So what are we getting then? What we are getting is the relationship that as one increases, the other decreases. So if you can reach here, then you have reached the relationship between the period and the frequency of the wave. From here, you can go on to calculate different expressions. From frequency, because we say it is the number of cycles per given second, then the SI unit of frequency, in this case we use, is Hertz. It is Hertz. And this we denote as capital H and small z. That z should be halfway, the h, for us to denote it or to take it as a small h. Take that seriously. Then, since period, we say it is the time it takes for a wave to make one complete oscillation. With the period, the SI unit we are going to use is a second, because we are looking at time. You can use small s. We have the wavelength. Wavelength, we've defined it as distance. So, with the wavelength, we are going to use a meter, because we are looking at distance. So this is what we want from you. Define these terms. As you're defining these terms, when given a question about the graphical representation of a wave, you should be able to define the different features on this graph. Features like the amplitude, wavelength, period, frequency. You have to also know what is a cycle, because waves move with cycles, repeat repeated, or what we call oscillations. You have to be able to derive the relationship between the period and the frequency. You also have to move on and derive or give us the SI units of these different terms that we've used: frequency, period, and wavelength. Thank you for attending this lesson. We shall take a short break, and when we come back, we shall continue from where we have stopped.